The narrative of infinite context is failing. In this analysis, we will dissect a fundamental vulnerability in today's leading AI architectures and examine the new paradigm proposed to solve it. This analysis will proceed as a 5-part investigation. First, the indictment, then the evidence. After that, we'll deconstruct the mechanism, analyze the cost, and finally, deliver the verdict. Section 1. The indictment. Here, we identify the core failure plaguing the current generation of large language models. The AI landscape is iterating at an unprecedented rate. But while major players release incremental updates to existing transformer architectures, a more fundamental shift is underway. Research from MIT has identified a critical vulnerability, a vulnerability they call context rot, and it affects all current models. So, what exactly is context rot? It is not a gradual decline in performance. It's better understood as a phase transition. Think of water suddenly freezing to ice. As information density and context length increase, the attention mechanism doesn't simply degrade, it fails. The result is a catastrophic breakdown in coherence and reasoning.
The industry promise is a 1 million token window. The reality? A drastic, nonlinear degradation of reasoning capabilities. For the information-dense tasks required in science, finance, and medicine, these models are proving to be fundamentally brittle. The advertised reasoning capabilities simply fails to materialize under pressure.
Section 2. The evidence. With the indictment made, we now examine the data that proves this failure. It is critical to distinguish between retrieval and reasoning. A model may find a single needle in a haystack, a simple retrieval task with a complexity of 1, but demand that it perform a quadratic reasoning task, finding all Olong pairs in a dataset, where complexity scales with the square of the input, and the illusion shatters. This is the torture test. 16,000. That is the point of failure. The data is clear. Even state-of-the-art models like GPT-5 begin to break down at just 16,000 tokens when subjected to these dense reasoning tasks. It's a mere fraction of their advertised capacity. Observe the performance collapse. At 16,000 tokens, performance on these quadratic tasks drops below 60%. By 33,000 tokens, it's near zero. The conclusion is unavoidable. Needle in a haystack is a marketing metric, not a reasoning metric. Section 3. The mechanism. Having established the failure, we will now deconstruct MIT's solution. The solution is a neurosymbolic system. This architecture doesn't try to fix the inherent flaws of a neural network. Instead, it combines the network's strength, pattern recognition, and fuzzy intuition with the rigid, verifiable logic of a symbolic system, in this case, code. The core insight from the MIT paper is a complete paradigm shift. The model is instructed to, quote, treat your long prompts as part of an external environment and allow the LLM to programmatically examine, decompose, and recursively call itself. It's no longer about passive consumption of context. It's about active interaction. The best analogy here is to think of an operating system for prompts. The full prompt is like a massive file on a hard disk. The LLM itself is the CPU. It can't possibly see the whole file at once. The Recursive Language Model, or RLM, acts as the operating system. It issues commands to read small pages of that data into memory, process them, and even spawn new subprocesses for more complex chunks. The process itself is entirely procedural. Step 1 is probing. The LLM writes code to inspect the data structure. Step 2, decomposition. It writes a loop to iterate over the context. Step 3, recursion. Inside that loop, it calls a fresh instance of itself on a specific, isolated chunk. And finally, step 4, aggregation. The root LLM collects all the outputs from these subcalls and synthesizes the final answer. Section 4, the cost. A new mechanism is only viable if its economics are sound. We will now analyze the performance versus price of this recursive approach. The data here is unequivocal. Let's look at the Olong Pairs task at 32,000 tokens. The base GPT-5 model achieves a performance of 0.04%. It fails completely. The RLM wrapped version, however, achieves 58%. And the cost? It merely doubles, from 16 cents per query to 33 cents. This is an almost unbelievable gain in performance for a marginal increase in price. As this chart illustrates, cost scales with complexity. Simple retrieval, the needle in a haystack, remains low cost. Linear reasoning tasks are moderately more expensive.
And yes, quadratic reasoning is the most costly. But the key takeaway is not the cost itself. It's that these complex reasoning tasks are now possible at a scale that was previously unattainable at any price.
And now for the fifth and final section, the verdict. What does this technological shift mean for the future of the AI industry? This brings us to a provocative, perhaps inevitable question. Is attention is all you need now obsolete? The foundational paper of the Transformer era appears to be insufficient for the next stage of AI. What we are witnessing is a fundamental paradigm shift from probabilistic to deterministic systems. Think about it. Retrieval augmented generation, or RAG, is probabilistic. It hopes a vector search will find the right data. The recursive language model, by contrast, is deterministic and exhaustive. It guarantees 100% data coverage because it uses code. It engineers a result rather than hoping for one. This leads to a new, more efficient division of labor. All reasoning is outsourced to deterministic code, in this case, Python. The neural network, the LLM, is then left to do what it actually does best: handle language, summarization, and what you might call fuzzy intuition. The outlook for 2026 becomes clear. The primary engineering challenge is no longer about extending attention spans. The new focus must be on optimizing the latency of these recursive loops. If that can be solved, this approach effectively enables an infinite context window for any reasoning task.
And so the final verdict is this. Neural networks are currently insufficient for precise, massive-scale reasoning without a symbolic exoskeleton to support them. They have reached a ceiling. To move forward, they require a structure for logic that they inherently lack. The future, it seems, is neurosymbolic.